Okay, so I'm going to talk about hybrid cloud. Don't worry about the costs that you might have seen on the previous slides. I'll give you a good discount. Just come to me at the end. So they asked me to speak about hybrid cloud because the reality is the way most of us are deploying cloud today is as a hybrid. So we're going to see some talks this afternoon on running cloud native experiments, a bit like the AWS batch that you've just seen. We'll see a couple of examples with Azure batch, Microsoft's equivalent. What I want to run through here is kind of the 101 of how you do hybrid cloud. And typically the journey that we go through with industrial customers, but also with research institutes and universities as they try to bolt one of the public clouds onto their existing infrastructure in order to be able to run research without having to learn all these new cloud native things that we've been showing this morning. So I think the previous presenter did quite a good job of talking about all the various blockers and pain points and sort of non-technical issues that you run into when adopting cloud services. When you're looking at building a hybrid cloud, there's sort of two sides to the challenge. You've got the researcher that just wants to run his work. He doesn't want to be a system administrator, doesn't really want to learn how to get good pricing in the cloud and do all this horrible IT, sysadmin type stuff. So we've got those types of users. And then we have IT, which have often no clue about the public cloud. They're happily running their high performance computing infrastructure, and really they just want to keep doing that. So how can we come up with a way of keeping both of those groups happy? And that's the hybrid architecture that I'll show you. So basically the question I get most of the time is, okay, we want to do cloud, but how do we go about doing that? And then some of the kind of things that we run into around data gravity, how do we deal with those? So you just had a mention of caching solutions, so I'll show you one of those that we have. If you look at the types of data sets that we're creating on premises and in the field at the moment, it can be hundreds of gigabytes to 10 terabytes coming out of an electron microscope now to tens or hundreds of petabytes coming out of a radio telescope array. So there are certain types of workloads that just demand, by the nature of the amount of data that they're creating, a hybrid infrastructure. So physics are not going to change, information theory is not going to change, we're not going to be able to compress those data sets massively. So a lot of the time we're going to have to deal with keeping those data sets on premise and bursting some of the compute for specific types of activities into the cloud to get access to all these goodies on the right that we have available in the public clouds like Microsoft Azure. So I'm just going to kind of run quickly through the typical journey that we go through with customers. So we'll typically see 2 or 3 phases as the universities start adopting cloud. So the first one is a little bit like the AWS example that you've just seen. So this is an experiment that we've been running with CHPC in South Africa, which is the national supercomputer in South Africa. So they wanted to start with cloud and figure out some way of how do we bolt cloud on to do things that we can't do on our existing cluster today. So they have a shortage of GPU infrastructure temporarily. So they were looking for a way of servicing a number of chemistry applications on GPU in the cloud. And the criteria to do this was they didn't really want the users to know that they're doing this. They wanted to make it very, very easy for the user to just run their application as if they were running it on the local cluster, but running on the public cloud. So the way we did that was using the Azure batch platform. Together with David McLeod from CHPC, we wrote a Python script which just talks to the APIs. So we have a budget sitting for CHPC in the cloud. We take CHPC's CentOS image with their chemistry applications compiled, built into the image, copy that into the cloud. Then as a user needs to run that application, he just types run my application, tells it where the data set is in a config file. It'll copy the data set into the cloud, run the job on the GPU nodes, and then push the results back out at the end of the job. So this is typically how customers start using cloud. So using it as a cloud native service. But the difference that we made here was to kind of hide all of that complexity of running the Azure batch stuff on the cloud native side. Another example of that, so the previous example was just targeting individual nodes. So often we want access to like a 128 core, 2 terabyte RAM system just to run a MPI job, or we want to run a cluster job. If we want something a bit larger, so we're going to run a massive parametric sweep job, for example, then Azure Batch is also a really nice platform to do that. So typically, just like the AWS description, we have a queuing engine there built in, so you don't need a separate queuing engine. So you package your application up. In this case, we just take a little bit of compiled MATLAB, we take the MATLAB runtime library, and then we can choose the format. We can either just zip it up into a zip file, an application package format that we can just upload to the cloud, or we can package it up in a Singularity or a Docker container using the Azure Batch platform, or using one of the projects that we have on GitHub that wrap around that as well. So once you submit your job, so it's literally just a config file, similar to the AWS stuff you saw. So config file, suite.json, that defines your job, how many cores it needs, or how many tasks are going to be making up the whole job. Each job knows where its input data is, typically in some kind of object storage pool or on a shared parallel file system, depending on the I/O requirements. And then with a single command on the user side from my laptop, I can run that job. So just push that in, push the data in. As it deploys, it'll do a Docker pull if I'm running a Docker container, or implement the zip file into the OS image. So in this case, it's a Linux image again, could be Windows as well. So my software gets installed automatically on each node, and then Batch, using the command line that I've inserted into the config file, will just fire that configuration out to 10,000 cores, 20,000 cores, whatever it is that you want to run. So as the queue starts to fill up, it starts deploying more and more instances of those VMs and containers, runs the job, and then as the queue drains, the jobs start to complete, then it shuts down the nodes again. So you're only paying for the compute that you're using, essentially. We also have things like preemptible instances, the spot instances. We also call them something different. We call them low priority VMs. So you can deploy the same GPU node or a CPU node for up to 80% cheaper using the low priority instance engine. That's just a flag that you set in the configuration file when you run the job. So the next phase, typically once people have started experimenting, they're doing some experiments with the Batch platform, people often become quickly interested in, okay, how do I build a cluster in the cloud like the one that I have on premises? And typically this is a tire kicking exercise. We basically want to get our application that we're running on premise, maybe running a CFD application. I want to push that over into the cloud, build a cluster just like I have on premise, and I want to see what the cloud can do in terms of performance and cost and some of the other metrics that we talked about. So the way you do this in the past was you'd have to code up all the infrastructure. So everything in the cloud is code. So every node, every NIC, every InfiniBand interface, every disk, everything is just code that I can define. So in the past, you would have to code that all up in a script and then go and deploy your cluster into the cloud. These days, we've acquired a company. I'm going to talk about a couple of the recent acquisitions that we've made. One of them is Cycle Computing. So Cycle Computing is a polycloud product. So their background is they manage clusters in places like NASA, so on-premise cluster infrastructure. They don't have a scheduler built in, so they can coexist with Univer or Slurm or PBS or whatever it is that you're running, but it'll manage the cloud infrastructure for you. So if I want to deploy a cluster in Azure, I can just go to the Cycle Computing interface. I can build out the type of clusters that I want in there from templates. So I could have a Slurm cluster with InfiniBand. I could have a genomics cluster just built on Ethernet infrastructure. So I can define a service catalog of different types of cluster with my applications pre-installed for specific projects or faculties or individual users. They can go into that portal, click on Go, and it'll spin that cluster up for them, run all of that code in the cloud to bring the cluster up. So it makes the whole business of deploying clusters in the cloud quite easily. Today it's still polycloud, it still talks to Google, still talks to AWS, talks better to Azure. We may continue that, we may not, I can't comment on that, but for now it's a polycloud product. And typically the users dealing here with the portal they have access to, cluster admins just dealing here, and you can create the clusters for the user and they can go ahead and deploy them. Submission mechanism is going to be very similar to what you're doing on premise. So you can use the same scheduler, just deployed as a different instance on the cloud side. So that's usually the first phase that we go through with customers of tire kicking. Does this cloud stuff really work? What's the performance like? So the next stage is then, okay, how do we make this a more permanent setup? So now we're happy with the performance. It looks like it can do what we want. I can bring my own operating system off my on-premise cluster with all my tooling, my modules, everything pre-installed. I can copy that over into the cloud, and now I can start building clusters from that. So usually the first thing that we need to do is to create the network infrastructure. So there can either be a VPN, usually as the first phase, and then we can have a dedicated higher bandwidth network if we need that later with an express route. And then once that's connected, you can really think of the clusters that we're building in the cloud are just an extension of the on-premise infrastructure. So I'm now, instead of submitting my jobs to the cloud, I'm just submitting my jobs as an end user exactly as before. So nothing changes. Just submit my job to Slurm or Univer Grid Engine or whatever I have. Cycle Cloud will pick up the job from that cluster, move the job over to the cloud, move the data with the job over to the cloud, run the job in the cloud, copy it back. And you can control that workflow through Cycle Computing. Cycle Computing, by the way, is free. If you'd like to test that out, if you want to do a POC with that, just talk to me at the end and I'll get you a license to do that. Storage is an important part of this as well. So I haven't been talking much about the storage, but when it comes to copying petabytes across the wire, there's no magic that works around that, but we do have some fairly neat solutions for at least making it optimal. So this is a bit of a busy slide. I'm trying to cram everything in one slide to just show you what the possibilities are when it comes to moving data around, storing data, pushing data in and out of the clouds. So when it comes to hybrid architectures, you've also got the possibility these days of having Azure Stack on-premise. So it means the infrastructure that you're running in the cloud, all the software infrastructure, deploying virtual machines, different types of compute nodes. You can also do that on-premise using exactly the same tooling, all the same types of features using Azure Stack. You can do remote visualization, so that's another way of cutting down the business of copying data back and forwards. So you can have GPU nodes in the cloud, leave my data sets in the cloud after processing, and then just do the visualization, send the pixels back over the network instead of pulling the data back to a high-performance workstation. Copying the data with the job. So if you look at a lot of these kind of scheduling vendors and cluster management vendors like Univer, Bright Computing, so what they've been trying to do is create more value than just being a scheduler. So they're trying to insert themselves between the cluster and the cloud and do these types of provisioning and queuing that we're also able to do with Cycle. 1 minute left to talk through all this. Isn't going to be a struggle. So we've got some tools that make that more efficient. So Bright Computing has something built into their tool. So it'll copy your data with the job, put it into the object storage in the Microsoft Cloud. Then it'll restore it onto a POSIX addressable mount point, typically an NFS server. So you can run your job, push the data back there, and then it'll copy the data back on premise. Cycle Cloud has something similar built in. It's called Pogo. So as you run the job, push the data over, you run your job, push it back. The problem with those types of architectures is every job you run involves a data transfer, and you don't have the same view of the namespace on either side of the connection. So if I want to tail my logs on a job that's running on premise, I just go to the project directory, tail the log. If I've pushed it to some unknown location in the cloud, first of all, I don't even know how to log into the cloud, and I don't want to know, and I can't tail my logs. So it's better to have a caching solution between the on-premise and the cloud, and for that, we acquired Avira. So that was just announced late last week. So Avira is a NAS caching engine. So we can basically have your NetApp or your open source NAS infrastructure sitting on premise, and then the same namespace will be mounted and presented through a virtual infrastructure in the cloud. So when I run my job, when I push the job into the queue that's going into the cloud, I can see all of the data, the files in exactly the same place, which means I can go over here and I can tail my logs exactly as normal. So I'm horribly out of time. Storage, I think, is a really interesting topic right now in the cloud. What you can see is everyone's trying to get access to this object storage stuff, but the problem is all the applications need a POSIX namespace. So we've got a couple of projects going on to address that. So Avira is one of those. The Microsoft Fuse driver is another one, so you can access the blob storage directly as a POSIX namespace from your application. I think there's a talk this afternoon on a different Fuse driver. And then we're even looking at, can we do things in the application layer with formats like HDF5? Can they address directly the layout into the object storage in the cloud? So that's all I have. The last challenge I always mention, because I want people to give me your thoughts on this when we have discussions during the breaks. The other challenge we have in cloud is bringing the applications to you. So Ulsa's Flight are doing a talk this afternoon. I think Ulsa's have a really nice solution for this. But where do you think Microsoft and the other guys should be investing to make this easier? So if I bring up this cloud, I've got thousands of applications in-house. How do I make them available in the cloud? Do I still want to maintain those as a cluster administrator, or should they be in container formats now? Should we be looking at OpenHPC as an umbrella organization to take that on? So I'd be interested in what you're doing to manage your application infrastructures for your end users, and how you see that going forward with multiple cloud infrastructures. So I'm done. Thank you very much.